for this, because we've done a lot of it already. So welcome. What we're going to do today is we're going to talk about AC theory. We did a little bit last time, and we'll review that, and then we'll just get stuck into it. It's very specific skills I want. So I'm kind of like trying to get to one circuit, which is the tuning circuit. And on the way, we're gonna do some stuff on AC. AC is a lot more than this, and it's kind of can be analysed quite sophisticatedly. We're making the first steps. So last time we spoke about how we can, if you have a coil or if I have a loop that's rotating in a magnetic field. So here's my magnetic field between these bar magnets. And I have this coil going round and round and round. What I will get is some kind of sine curve. Well, it's sine or cosine depending upon where I take the starting position. It's just that when I start. But I'm going to start it in mathematically. I'm going to assume I always start with it in the zero position. So this might be voltage, and this will be time, and I will see this nice sine curve. And if I, for instance, put that through a resistor, then in time, what I'll see for my current is, again, a sine curve. Might have a different amplitude, because numerically the number of volts doesn't equal the number of amps, depends on the resistor. But when one's maximum, the other one's maximum. When one's negative, the other one's negative, they follow each other. That might seem like, obvious. Of course they follow each other. But for other components, that's not the case. So I can express this by a maximum voltage modified by a sine of an angle, and the angle is omega t. And we did that with oscillations and waves. We talked about how we can talk about an angle in terms of radians per second times seconds. So that's where the omega t comes from. And I could call it theta, and I could have it in, hertz per second times seconds. I can play that game, but let's just leave it in omegas. Just remembering that omega is equal to 2 pi times f. So if I want it in hertz, I can rearrange to get it, in hertz. It's no big deal. And I think I pointed out last time the fact there's a mistake on this, because really, there's a mistake in the wrong bit. So really, so there's the beginning point, and then here's the first maximum, which is there, and then here's the second 0 point, and here's the first negative maximum, which is there, and we're back at the beginning. So that one wave can be represented as one cycle, and because it repeats, I can just do cycle after cycle after cycle. And this is a phasor, and phasors are really useful. I'm going to just see them a little bit, but phasors are really useful. And what I say is, well, okay, the y measurement is the same, it's just how I represent the position, really. And I meant represent the position wrong on this one, because this is before you get, A comes before you get to the maximum, and because I'm going that way around, then my A would be here, not over here. I just drew it badly. But my B is okay. My B has the same height, and it's, before I get to the 0, and then my C is between the 0 and the negative maximum, and then my D is over there. So it's just a very nice representation. And yes, if you're like me, you'd look at the phasor and go, do I really need this? Not catching on to the fact that the only reason it's in the book is because it earns its way. It is really worth it. It's like numbers are really worth it. When you first learn them, it's a real pain, But, man, they pay off dividends later on. So if it's in the book, it's really worth it. Okay, so then we talk about, we can talk about phases, or we can talk about the actual wave. But here's a problem we have with alternating, and that is the fact that when I average alternating, I always get 0. And I'm looking at current here. So imagine the situation where I have, 1,000 amps oscillating through. What does that mean? 1,000 amps flows that way, and then 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 flows that way. So the electron doesn't make it from my battery to the light. It would in DC. In DC, the electron leaves the battery, goes along the wire, goes through my light, causes heat, causes light, goes back and gets some more energy and goes around and around and around again. In AC, the thing that's moving backwards and forwards is the electron that's already in the light, and the electron that's in my generator stays in my generator. It's like a bicycle chain. It's like going like that on the bicycle, for a fixed wheel bicycle, going that way on a bicycle chain, and your back wheel moves like that. You know, that little loop on the chain never makes it to the back wheel. Doesn't have to, because when you're doing AC, now you don't go very far when you pedal your bicycle like that. But imagine, well, you know, if you want to cut down a tree, we could have a really long saw, and we could just push it through for like 3 days, so it's as long as, you know, the state is, and it'll cut through the tree. Or we can take a little saw and just go backwards and forwards. Does the job. So AC is kind of interesting. It's the electrons in the generator that push the electrons in the wire, that push the electrons in the wire, that push the electrons in the wire, that pushes the electrons in our component, which pushes and so on. But the energy is kind of transferred, so it works. Can you imagine having 1,000 amps flowing this way through you, and then 1,000 amps going that way through you, and then 1,000 amps going this way, and 1,000 amps going that way, and then I turn around to you and say, well, on average, there's no current going through you, so you should be okay. I mean, you'd be like a briquette by the end of it. You'd be so burned, it would be untrue. But on average, no current went through you. So that's a craziness. That's just nonsense. So what we realize is with these symmetrical oscillating signals, the average is pointless. And yet, you know, there is a difference between having 1,000 amps going through me backwards and that didn't work. 1,000 amps going through me backwards and forwards, and having, you know, a milliamp going through me backwards and forwards. It makes a difference. And so I need to characterize that somehow. By the way, there's a little adage I'd like you to just remember, and that is volts, voltage, volts, jolts, current kills. Now, the bigger the voltage, the more current you get flowing. So high voltage can lead to high current. But it turns out, like with a Van de Graaff generator, with a high voltage power supply, it might not have much power. And so although it's like 30,000 volts, if there's no current allowed out, if it cannot produce that voltage at that high current at that voltage, even though the current could flow through you, there's not enough current to do you damage. So you're saved by the limit of the actual machine. But if I could turn up the current on that machine to let more and more go through, it'd be very dangerous. And the problem is, when you get into high-powered research machines, then they want the current because they want the power, you know. They want high voltage and high power. So those machines are really quite dangerous, and the technicians and the engineers that work on those machines are quite specialized. They learn it throughout their career, or they quit because they've had like a hair-raising experience they don't want to repeat again. It's one of those things where if you're a bit slapdash, you need to get out of that field. But you find they do things like, I remember just the people in the electronics workshop when I was a student, you could tell them just by looking at them. First of all, they were all full of themselves. They knew a lot more than anybody else did about what they. It's a bit like computer people now. If you get a computer person, they kind of talk down to you a bit. I'm a professor, and this guy's talking down to me because I don't know the secret code to. I mean, it took me 2 days to get my phone to connect back to the wireless system, and then when I found out how to do it, it was pretty straightforward. It's just not written down anywhere, you know. But so when you got specialized skills, you tend to get a bit full of yourself, like, you know, I'm full of myself because of physics, you know, etc. So it used to be like that with the electrical people, because they were like full of themselves. They did dangerous stuff and they were good at it. The other way you could tell them was because they all wore, do you know what Doc Martin boots are? Do they still have them? They're really thick-soled leather boots. with big rubber soles. And the reason why they wore those was because they're extra insulating. That's kind of nice, you know. And they tended, it was the weirdest thing. They worked, and there was always a hand in their pocket. It's like the first thing you're taught as an English kid is you take your hands out of your pockets. And they talk, and they're pointing, and they're picking stuff up, and this hand is never leaving this pocket. It's the weirdest thing. And then you find out, yeah, because that kills you. If I touch something that's high voltage and it's potentially high current and it goes through, it's going to go down one side. It might give me a heck of a shock, but that will take it right across my heart. And that's when I die. So they've been trained, you know, they put their hand in their pocket, so they're much less likely to grab two things. So volts, jolts, current kills. A car battery in many ways is a lot more dangerous than a high voltage power supply. Now normally it's only 12 volts and it's dry, and you know, you can touch the terminal and you know, chances are you'll be all right. You try not to, but you know. But I tell you, when it's raining, if you break down and it's raining, if it's raining hard, so when you lift the hood up, that area gets wet. Be very, very careful. I would, frankly, I would wait for it to stop raining. Because when there's moisture around and when you're wet, then things get serious and you get wrapped up in things. So I bought my own house. I bought a fixer-upper, and I had a concrete floor. It was a terrazzo floor. And when they polish the floors, they kind of like, they grind it, and it's not necessarily flat. It's like, not obviously not flat. And it happened that in the closet where they put my AC system, it was a bit of a low point. And I had a problem with the sump pump, the pump that takes the water out of there's a little pan under the compressor, under the AC, which catches the moisture. And then it's supposed to, every now and then there's a little sump pump where it says, oh, you're full, I'll basically pump you outside. So there's a little sump pump, and that wasn't working. So I'd come home, and the thing, my living room would have like water in it. And oh man, that problem has happened again. And I think I'd fixed it, you know, and I wouldn't have fixed it. And you get rattled by it. So I remember coming home and seeing this, oh, again? So I went to my bedroom and I got changed. So I put shorts on, I put a t-shirt on, and I couldn't find my flip-flops. So I just patted along the room, and I'm stood, and I've got a voltmeter in my hand, and I want to check, is there a problem with the power supply? And there's two little wires, and I take the little nuts off, the wire nuts off. So I've got two live wires. And I've got my meter, I'm holding my meter in one hand, and because I've got meter in one hand, I've got to get these two probes, and you hold them a bit like chopsticks, and you're trying to push them towards the two wires. And as I'm doing that, I'm thinking, man, that water's cold. And I realize I'm stood in water trying to test to see if this cable is live. And I got a PhD. And it just struck me, the headline, you know, PhD, electrocutes himself, standing in a pool of water. And I wasn't thinking it through because it was like I was wrapped up in it. So watch out. Volts, jolts, current kills, and just, you know, be respectful. Don't be scared of it. Learn what you need to learn. If you're doing electronics, not so different. It's a different area. If you're doing power, electricity, then you got to be much more careful. So this is not going to work. This idea about having the average value is not going to work. So what can we do? The problem is we have an equal amount of negative flowing current as positive flowing current, and that's what's cancelling us out. So the first thing to do is to square everything so it all becomes positive. Now I can mean it or average it. And then the problem is it's too high a level because I squared everything. So then I undo the squaring by square rooting it. So I go, well, I squared it, and I meaned it, and I rooted it. And so for some reason we call it the RMS. The root mean square, not the square mean root. And I don't know why, but we call it the RMS. It's just a simple way of getting a value which is indicative. Because here's the issue. If I have a voltage versus time relationship and a current versus time relationship, and I use P is equal to I delta V. Remember what we said for power? This is power, joules per second. If I take the maximum voltage and the maximum current, it's only at those two values for an instant every cycle. Most of the time it's much less than that. So it's unrealistic to take the peak voltage and the peak current. And so for this, you need, for power in AC, you need the IRMS and you need the delta VRMS. So that's specifically where you need it. When you do the IRMS and your delta VRMS and you measure the power given off by a resistor, it's right. You get the right number. But if you use the peak and the peak, you're not going to get the right number. Now, frankly, when I say delta V equals IR, the equation does not care if I'm using peak or RMS. So I can say delta V peak equals I peak times R, and that's correct. And I can say delta V RMS equals I RMS times R, and that's correct. So Ohm's law, it doesn't matter as long as you stick with what you've got. But with power, you need to be in RMS. Okay. So that's what this basically says. And the RMS is basically the maximum value over root 2 because of the shape of this thing. It's the maximum value over root 2, which is 71%, basically. So if we do this, we can say an AC current has an amplitude of 10 amps. So that is 10 amps. And so what's the RMS? IRMS equals I max over square root of 2, which equals 0.71 times I max, which equals 7.1 amps. Simple as that, really. It's no big deal. If I have a slightly bigger voltage, so this here is 15 volts, then VRMS is equal to V max over the square root of 2, which equals 0.71 V max, which equals, it's going to be 7.1 plus 3.55 is 10.65 volts. So not bad. If you want to know the power is equal to V max I max, which would be whatever that works out to be, you know. It would be 7.1 times 10.65 equals be 75.6 watts, which is 75.6 joules every second. Cool. You didn't ask for that, but if I asked you for it, that's how you'd get it. Cool. Cool. Now, not every signal is AC. Sometimes you get square waves, sometimes you get triangular waves. That's a different issue. We're talking about the sine wave you get, or you create. You get it by rotating the coil inside a magnetic field, or you can synthesize it. Okay, so that's that. So then the next thing is, I want to teach you the background to the tuning circuit. The tuning circuit is the circuit we use in radios. Now, this is if you like, this is the original tuning circuit, and it don't work that great, but it's all right. Much more sophisticated now, but this is all right. And the tuning circuit is basically that circuit. It's some kind of oscillator, and for us, we could imagine that being a radio station, and it's sending a signal into an antenna, and that signal is then fed through an inductor, a resistor, and a capacitor. Now we're going to show it because we don't want to mess with picking up a signal. We're just going to connect the signal to it. So we have a function generator, and we could just connect it to the circuit. But our function generator in the lab yesterday was kind of behaving like a radio station. And if we wanted to see the practicality of it, we'd simply take this and we'd put it, for example, into a speaker, and we'd hear the music or whatever. That's basically how that, in principle, that's how that works. And it seems simple enough, except that there's a couple of little things that make it a bit less simple. We're used to the idea from DC circuits that the voltage drop across the inductor will not be the same as the voltage drop across the capacitor, which will not be the same as the voltage drop across the resistor. We've seen that before, yeah? We saw it with the capacitor-resistor network, where at the beginning all the voltage was across the resistor and none of it was dropped across the capacitor. And at the end all of it was across the capacitor and none of it was across the resistor, yeah? We've seen that before. So we're used to the idea that the voltages, the potential differences on this side must add up to the EMF on that side. We did that in DC circuits, yeah? Now the wrinkle is that the EMF is changing in time. Yeah, whoa, that's like, man, that's going to be complicated. But what we can say, remember, as engineers and physicists, we're always looking for what's the same. We want equations which is equal sign. An equation says, what's the same as this? That's what an equation says. So we're always saying, what's the same? What's the same on this is the current flow. The current flow through the inductor is the same as the current flow through the resistor, which is the same as the current flow through the capacitor. I know it doesn't really flow through the capacitor, but, you know, in effect it does. So we know the current flows are the same. So later on, when I'm trying to add up what happens with this circuit, I'm going to look at the current flow and say the current through there is the same as the current through there is the same as the current through there. That's my safe knowledge. Now, I tend to talk about this as an LRC circuit, whereas if you look in the book, most times you see it as a RLC network. And I don't like that. It's not that that's wrong. They were there before I was, you know. I mean, it's just... But, see, what we're going to find out is that in the physics of this, the inductor voltage leads, and I'll explain leading in a minute. The inductor voltage leads the resistor voltage, which leads the capacitor voltage. I know that sounds weird, but I'll explain it in a minute. And so when I say LRC, I'm always reminding myself, oh, the inductor leads, the capacitor comes second, the resistor comes second, the capacitor comes third. So I'm reinforcing this order of things. But I need to justify what this leading business is. So we've got to go back for that. So let's take the thing we're most familiar with, which is the resistor. And let's just imagine connecting up an oscilloscope, a voltmeter across here and a voltmeter across there. And we'll look at how the trace of the voltage varies with time, which is what an oscilloscope does. And we see, put them both on the same graph. They've got different magnitudes because, I'm going to look at my current through here and my voltage across there. And I'm going to put them on the same graph, and they're going to have different numbers. You know, in this case, I got an I that's bigger than a delta V. There's no significance to it being bigger. It's just that I happen to use a resistor, which gave me a numerically bigger value for I than I have for my voltage. But I could have used a different resistor and reversed it. So there's no significance in the relative sizes. It's just that they are different. And the significant thing is that when one of them's zero, the other's zero. So when your voltage is zero, your current is zero. When your voltage is a maximum, your current's a maximum. When your voltage is zero, your current's zero. When your voltage is a maximum negative, your current's a maximum negative. When your voltage is zero, your current's zero. They are in phase. Remember that from sound? We had these things, that's in phase, that's anti-phase. These guys are in phase. This is a pretty easy trace to look at on the left-hand side. You can tell what's going on. I can pick a certain point. So I pick that time. Remember, it's time, and then it's the two scales, voltage and current, vertically. And that's pretty well easy to interpret. But there is, and we'll see in a minute, there is an advantage. There's a clarity that comes out of plotting these things as phasor diagrams. So here's my y height is the same, and they've both gone through the same time, so they're both the same distance, they're both the same proportion through the cycle, which is the same angle through the cycle. Remember that cycle is 2 pi radians in terms of radians from there to there. It's one period in terms of time, but it's 2 pi radians, and so that's one circle, and they're both the same distance around the circle, both the same angle around the circle. That shows you that they're both in phase with each other very nicely. And over time, they'll end up pointing in different directions, but they'll always be in line with each other. Yeah, they're always going to be in line with each other. They'll have different values, that one and that one, and that one and that one, and that one and that one, and you know, but they'll always be, on the phasor diagram, they'll always be on the same line. I can develop this relationship, which I'm familiar with. The current at any instant is equal to the voltage at any instant divided by the resistance. Resistance is constant. Or the current, or the maximum current equals the maximum voltage divided by the resistance. It doesn't matter, maximum or not. It's, you know. Okay. Ohm's law, this is just Ohm's law, I'm familiar with that. Okay, that seemed okay. A bit mathematically, the EMF plus the voltage drop across the resistor sums to 0. Whose law was that? Which law am I invoking when I say the EMF plus the potential differences sum to 0? We did it. Pardon? Kirchhoff's laws. Yeah, that's Kirchhoff's laws. So knowing Kirchhoff's laws, we can say, well, those two, that's equal. And then we say, well, you know, this is a varying voltage. And what is it? Well, it's V max modified by the sine of omega t. And then I say, well, my current is equal to V max over R, which is I max sine omega t. And what I want you to look at is the voltage is a sine omega t, and the current is a sine omega t. So for any time, they both have the same omega, of course. For any time, they stay in phase. Agreed? That's mathematically how I show they're in phase. There's the diagrammatic version down here, but I can prove it mathematically by looking at those two. Yeah? Because later on, it's not going to be so obvious, so I need to rely on being able to interrogate those two things. So let's do the next thing, which is an inductor. Okay, this is a little bit more difficult, and you don't have to reproduce all this. I'd like to just guide you through it, and I'll show you which bits I need you to know. EMF is equal to the voltage drop across the inductor, and the voltage drop across the inductor, of course, is minus L di by dt. Oh, by the way, in AC theory, they sometimes, rather than saying IAC, they say little I. And if you're not careful, what does that remind you of? What is little I? When you see little I, what do you immediately think of mathematically? Imaginary numbers. And does it make the hair on the back of your head stand up? It's like, you know, I mean, you know, a glance, a casual glance, you go, oh my word, there's complex numbers in here. They're not. It's just, sometimes they're called the AC I to distinguish it from the big I. Either way, I don't care. So minus L di by dt equals 0. And I remember, of course, that my time-dependent voltage is V max sine omega t. And so I substitute in. So I say, well, L di by dt, that's that bit, is equal to that bit which is Vmax sine omega t. And so I do this trick where I take the dt to the other side and I go di is equal to Vmax over L sine omega t dt. Then I say, oh, well, I can find what the total current is by integrating. So I get my total current by integrating. Well, the Vmax is a constant, so that can come out. And the L is a constant, so that can come out. So I have the integral of sine omega t dt. So that becomes cosine omega t. Ooh. So it's a minus Vmax over omega L cosine omega t. Well, that is being compared with that. And they are not the same anymore. Back here, they were the same. Yeah. Back here, that is a sine omega t, and that stays as a sine omega t. But now, that's a sine omega t, but this is a cosine, and a negative cosine omega t. Okay, just fell out of the math. What does it mean? Well, if I remember a bit my trig identities, then cosine omega t is minus sine omega t minus pi over 2. I need the minus pi over 2 because that's a minus there as well. So, okay, fair enough. When I substitute that in, I'm comparing that with that. And what I see is that these are out of phase. And can you see that tells me the negative pi over 2 tells me, because that's the same as that, the negative pi over 2 tells me that my current lags the voltage by 90 degrees. Pi over 2 is 90 degrees. So if I draw this out on a phasor, that lags by 90 degrees. Comes out of the math. When I put the amp and the voltage, what I see is it looks like this. My voltage is just as it was before. Now my current is lagging. The peak comes a quarter of a period later. Everything's a quarter of a period later. And I can kind of like get this to a little extent. If I say, well, remember this is a di by dt. So when my current is not changing, I expect a 0 on that. When my current has a big positive change, I expect a big positive number for that. When my current has a big negative change, I expect a big negative. So I can hand wave my way through it. But this is mathematically showing it. Now, you know what? I like this idea about using the Ohm's law. So I max was equal to delta V max over R. Can I do something similar for this? And so I look and I say, well, we're talking about maximums, so let's just make that equal to 1. So I can say, well, yeah, if I call omega L R, I get that same expression. I is equal to delta V over omega L rather than over R. So maybe I can make up a new term, and instead of R, I have this thing called reactance. Not resistance, but reactance. And it's given the symbol X. And I have an inductive reactance, XL. What were the units? What does your gut feeling tell you, given the job that XL is doing? What units do you think XL should be in if it's kind of playing the part of resistance? No, it's not a sneeze. No, what would it be? Ohms. It's ohms. It's the resistance that's caused by the reactance. Now here's the catch. Why don't they call it inductive resistance then? And the problem is, can you think of why you can't call it inductive resistance? Because your inductance has a resistance. It's a piece of wire, isn't it? So it's got resistance. So we can't have two things used by the same name. So we don't call it inductive resistance. We call it inductive reactance. Okay. What can you tell me about how the inductive reactance, the resistance to the flow of current through an inductor, what can you tell me about how the inductive reactance changes with the frequency of the signal you're trying to put through the inductor? What can you tell me about it? What can you tell me about how that changes with that? What kind of graph would you draw? Ohms and omega, and what would it be? And what would the slope of this graph equal? The L, which is your inductance. What this tells you is that at high frequencies, this inductor is going to kill your current. So a radio station which tries to drive your radio at a higher frequency than the natural frequency of this LRC network, that radio station, although it's picked up by the radio, by the antenna, produces no significant current going through the circuit to be amplified, to be listened to, because the inductor is killing the current, because the inductor is harder and harder on higher frequency current changes. So the inductor kills you at high frequencies. So what do you need out of this? I need you to know this equation, and I need you to be able to talk about it. You know, it's linear. You know, omega, XL versus omega is linear, and the slope is the inductance. And it kills you at high frequencies. I need you to have that familiarity with it. But the question I'm for sure going to ask you is, what is the reactance of an inductor, of this inductant, at that frequency? I'm going to ask you that question. You're going to do that calculation somewhere. So that's what you need to be able to do. And I'd also like you to know, for example, now I'm going to change this around a bit. What we said was that the current lags the voltage, because that's the way it came out mathematically. But the significant thing is that the voltage is leading the current. Remember, the current is the same through all those components. So rather than saying the current lags, I'm going to say the voltage leads. Let's think about a capacitor. Capacitor, again, the EMF is equal to the voltage drop across the capacitor. And so they're equal to each other. And for the voltage drop across the capacitor, VC is equal to Q over C. And of course, V is equal to V max sine omega t as usual. So this is V max sine omega t is equal to Q over C. So C V max sine omega t is equal to Q. And of course, your current is dQ by dt. So just differentiate this. So we just differentiate that. And when we look at this, we see that this is a cosine omega t, and that's a sine omega t. And so we've got to do this rearrangement. Oh, yeah, I get it. A cosine omega t is sine omega t plus pi over 2. There's no negative sign to mess me up this time, so it's plus pi over 2. Oh, so that means that this current is in front of my voltage. That's how it comes out mathematically. This is in front. This one was behind. This is in front. It's the opposite. And, you know, you can hand-wavingly justify that by saying, you know, when you have the maximum charge on the capacitor, you have no current flowing. actually. Is that going to... So my... let's have a look. I got to think this through. I'm sorry. So let's have a look. When my voltage across my capacitor is the biggest, I get no current flow. So I got that bit out. When my can I do better than that? When my current flow is flowing in a... No, that's about as good as I can do today. Okay. It comes out of the mouth. So when I do my phasor diagram, I draw it like this. Now remember, we're going to link the current to all these three things, so I prefer to say that the voltage is behind in this case. L, R, C. The voltage is behind, the voltage is in front, the voltage is where it should be. Yep. Again, I say, is there any way I can get an equivalent for resistance on this? Well, this is a little bit, let that go to 1. So this is going to be IC equals delta V max. Now, oh man, I can put an XC there, but XC is not equal to omega C. XC is equal to 1 over omega C. Just mathematically for that to work out. So now if I do ohms versus omega, I get the inverse relationship. So the capacitor kills you at low frequencies. So if you have a radio station that's trying to drive your radio at a frequency that's lower than the setting of your radio, although the signal is picked up in the antenna, any current that's causing to flow through your circuit is pinched away by the very high capacitive reactance. So the inductor kills your high frequency stations and your capacitor kills your low frequency stations. And if I put those two guys together, so here's my resistance for my circuit. This is a bit hand waving. I've got to be a little bit careful here. Then I have that and I have that. And there's a sweet spot in the middle where my resistance is a minimum. And that's frequency. The frequency that causes that is my tuning frequency. When I turn the knob on the radio, that's what I'm adjusting. And notice, it's not that you have no resistance in your inductor and no resistance in your capacitor at that time. It's just that you got a minimum in your circuit at that time. So we need to... So what do I need to know from there? I need to know, that the voltage is behind. I need to know how to work out XC. I need to know how to draw that kind of thing. I need to know that kind of stuff on there. What is the reactance of a 5 Henry inductor when a 5 radian per second, so let's do the inductor, it's like a little coil, and this is 5 Henrys, and this is, I'm sorry about this, 5 radians per second. What's the symbol for the frequency in radians per second? What do I call that in my equations? Well, frequency, what letter do I use for something that's 5 radians per second? What symbol would you put down for? Oh, that's a... Is it a V? Is it an I? Is it... What is it? Omega. Yeah, omega. Yeah. So my L is equal to 5 Henrys and my omega is equal to 5 radians per second. And what do I know? What is the reactance? So XL is equal to omega L, which equals 5 times 5, which equals 25. And what units will this be in? Ohms, yeah. So now I have a 10... I've got a 10 farad capacitor. That's a huge capacitor. Now this is 54 hertz. Oh man, that's a bit of a... Now I just remember that omega equals 2 pi times F, so F is equal to omega over 2 pi. What's the equation for XC? It's the 1 over something? 1 over omega C. Which is 1 over omega. Well, that's going to be, omega is going to be equal to 2 pi times 54 times C, and C was 10. So I'll get my calculator. And I go 2 times pi times 54 times 10, enter. And then, yeah, don't forget to flip it. That's going to be 2.9 times 10 to the minus 1, 2, 3, 4. 10 to the minus 4. What the unit's going to be for this guy? Ohms, yeah. And on the last one, and this is 10 ohms, and this is 25 hertz. And what's my R? What's my resistance? What's the resistance of a 10 ohm resistor at 25 hertz? I'd offer you Halloween candy, but you're probably all as sick of it as I am. So. What's the resistance of a 10 ohm resistor at 25 hertz? You know this. You're forgetting how nasty I am. What's the resistance of a 10 ohm resistor at 25 hertz? How many ohms is it? It's 10. Yeah, there's no frequency effect on the resistor. There is on the inductor, there is on the capacitor, but there's not on the resistor. So it's just always 10. And people forget that. People, they get into a mindset and they're lost in the math. And so they're kind of like looking for something complicated. But it's just 10. Yeah, it's just 10. Okay, so a typical question would give you an inductor, a capacitor, and a resistor. Fellas, please. And it would say, what is your inductive reactance or what is your capacitive reactance at this given frequency? You've got to work it out. And then either with that same problem or in the second problem, I would give you an inductor, a reactance, and a capacitor. I'm going to ask you to do the next bit, which is to work out the impedance. I need to explain what impedance is and where it comes from. It is the overall resistance of the circuit at a given frequency. It's the net effect. So what the heck's going on? Well, we know we have a certain amount of applied voltage at any instant, and we know that there's a little bit across there, and a little bit across there, and a little bit across there. And when we use our graphs to spot these things up, then yeah, okay, we find that at that point there's that and nothing, okay. And over here, we'd have that cancels out that and nothing. And so there's this complicated pattern. And you can't really see it from here of how these things are interacting. Because this is just, it's correct. These are correct traces, but they're not clear traces. And I can say, well, look, the voltage across the resistor is I max times R, and the voltage across the inductor is I max times the inductive reactance. And I can say the voltage across the capacitor is I max times the capacitive reactance. And I can tell you what the equation is for your voltage at any given time. And, you know, yada, yada. You can work these things out, and it still does not, it's not clear. But this is. And what this says is the current through all these components is the same. When the current is big in one, it's big in the other, it's big in the other. When it's none in one, it's none in one, it's not. When it's minus in one, it's minus in one, it's minus in the other. The current is the same. That's the link. And what we learned was that your inductor voltage is 90 degrees ahead. And we learned that your capacitor voltage is 90 degrees behind. And we learned that your resistor voltage is in phase. Now, I can't add those up arithmetically because they're pointing in different directions. I have to add those up vectorially. And so I say, well, my net voltage is equal to the sum of these two on the vertical axis added to this one on the horizontal axis. So I get a Pythagorean triangle, yeah? And so I've got to add things vectorially. Okay, I'd like to know the resistive effect of this circuit. That's what I'd really like to know, because when that's a minimum, I get my maximum signal. And when that's high, I'm killing my signal. I'd like to know how the total resistance changes with frequency. Oh, in that case, we simply add our resistances and reactances. And so the diagram I prefer, which I'd like it to be able to do, is you're going to say that this is XL, and you're going to say this is XC, and you're going to say this is R. And then from that, you're going to say, well, that means that I have this guy, which is XL minus XC, and we have this guy, which is R, and my net effect, my Z, is the Pythagorean or the vector sum. So I can say that Z, this is my impedance. My impedance is equal to the square root of R squared plus, well, it's going to be the square of XL minus XC, all squared. And I can define my angle as being the opposite over the tangent of the opposite over the adjacent. And I can say that my maximum voltage is equal to I max times Z. So a typical question would be, I give you an omega, I give you an R, an L, and a C. I ask you for XL and or I ask you for XC at a given frequency. I might ask you for R at the given frequency to see if you're thinking it through. I could ask you conceptually which leads, which lags, all that. I ask you to draw that and calculate Z. That's a typical sequence. What's the XL? What's the XC? Can you draw me the phasor diagram? Can you work out what the impedance is at this frequency? That's a typical pattern. Might not all of it, but you know, you're going to end up stepping through it. Sometimes I find it good to have one set of values which take all the way through. If you make a mistake, you tend to carry it through. So for me, for grading, it takes a bit hard. Or other times, I'll ask you to find an XL, and then on another bit, I'll say, what's the Z, with different numbers. So the two are independent questions. That's the skill. So just ask yourself now, can I work out what my XL is? Can I work out what my XC is? Could I work out what the Z is? It's not hard. Mathematically, you know how to do this. It's just, do you know the equations and do you know the diagrams? Okay? How am I doing? Almost. Okay. So, I can look at this and I can say power in an AC circuit, no power losses associated with pure capacitors or pure inductors, all the power losses because of the resistor, and I can play a game with that, and what I end up with is that the power loss equals I squared R. So that's something worth knowing, I squared R. And if I do what we did in class the other day, and I plot out some nice graphs for a given L and a given C, if I change my R, I go from a broad value at a high value of L to a sharp value at a low value of R. Sorry, this is a wide value at a big value of R and a small value, a narrow value at a small value of R. If you think about it, when you're at resonance, when you're at the tuned frequency, these two reactances cancel each other. They're not zero, but they cancel each other out. So your Z is equal to R. Z equals R at resonance. If I make R smaller, I get a sharper peak. I can define well, I'm not going to get there yet. The resonant value of your circuit depends upon when XL equals XC, which means omega L is equal to 1 over omega C, which means that this omega is equal to 1 over LC. Know that. Know how to determine the resonant frequency of your circuit. There's engineering expression which defines, it's a figure of merit for the sharpness of your peak, and it is the width divided by the total value. I wish this went down to 0. It's bad representation here. So it's whatever your omega is divided by whatever your delta is. It's called a Q factor. I don't care so much about that. I want you to know it's there. Don't learn it for the test. Okay. Final little bit. I'm just going to mention this so I can finish off the tape and then we'll. On a different tack, the reason why we like AC so much is because we can use transformers, mutual inductance. The key equation for mutual inductance is the ratio of the turns is equal to the ratio of the voltages. They tend to not show it. They tend to show it in these other ways. But the ratio of the turns equals the ratio of the voltages. And the power on this side equals the power on that side. So the power on the primary is equal to the power on the secondary. So know that and know that. And we'll go offline now and we can do some examples.